We now come to the Riemann-Lebesgue theorem. We are going to completely characterize precisely which functions are continuous. Then we are going to give a huge list of corollaries. Pretty much all the major theorems of Riemann integrals will follow from this theorem. Now, in traditional treatments at the undergraduate level, this theorem is usually skipped, and instead these properties are proved directly by using the condition that function is integrable if and only if u of fp minus L of fp can be made less than epsilon. Now, the reason why I have preferred to prove the Riemann-Lebesgue theorem, whose proof, by the way, is quite challenging, is the following. There is a deep idea behind the proof. And as we all know, ideas are bulletproof. This idea in various forms is there in the proof of the various properties. By centralizing all the deep ideas into one theorem and understanding that once and for all, we have economy of thought. You just have to understand this theorem and everything about Riemann integration will follow from this. So what is this deep idea that I'm talking about? It's essentially this summation mi minus mi, capital Mi minus small mi, delta xi. We want to make this small. For each epsilon, if you can find a partition such that this is small, then the function f is integrable and vice versa. Now, there are two obstacles to this sum being small. One is that this could be really large. This capital Mi minus small mi could be really large. Second is that this could be really large. But notice that we have full control over this delta xi, right? We choose the partition. The statement of the characterization of Riemann integrability is that given any epsilon greater than 0, we can find a partition P such that summation capital Mi minus small mi delta xi is less than epsilon. We have full control over this delta xi. Therefore, what we are going to do is we are going to delicately balance this quantity, which could be large at some places, and this quantity for which we have full control. So the essential idea is the following. Let me first state the theorem so that I'm not thinking out aloud in air. Let me have something concrete in front of you and me. Theorem, a function f from close AB to R. Let me add a bounded function, of course. A bounded function is Riemann integrable if and only if the set of discontinuities of f is a set of measure 0. Now, away from the set of discontinuities, we have control over this capital Mi minus small mi. We can make it as small as we desire by shrinking the intervals, right? The key is at those points of discontinuity where the function's oscillation is going to be greater than 0, we control capital Mi minus small mi delta xi by making delta xi really small. And we can do this because the set of discontinuities is a set of measure 0. Therefore, you can cover it by as small open intervals as you desire. So that is the key fact. So let's begin the proof. And please keep in mind these vague remarks that I am making. You will see these vague remarks coming in front of you alive. So let us assume f is integrable. Okay, the set of discontinuities D, let's call it D, is actually going to be equal to, you can break it up as, we have done this before, as union of dk k running from 1 to infinity, where dk is just the collection of x in 0, 1 such that oscillation of f at x, or I think the notation was oscillation at x of f is greater than or equal to 1 by k. Okay, look at the set dk, which is the set of points not in 0, 1. Sorry about that. It is AB, x in AB. Look at the set of points where the oscillation is greater than or equal to 1 by k. Call that set dk. D naturally decomposes as the union of the various dk's. Okay. Now, suffices to show each dk is a set of measure 0. Recall from the previous module that a countable union of measure 0 sets is a set of measure 0. This follows by an epsilon by 2 power n trick that we have already seen. Okay, we are going to show that each dk is a set of measure 0. So what we do is the following. Let P be a partition such that U of Fp minus L of Fp is less than epsilon by k. You will understand why I am putting this k in the denominator. This k is the same k here. We are going to show that each dk is a set of measure 0. So I should say fix k in n to be concrete. Fix k in n. I am going to show that dk is a set of measure 0. Choose a partition such that fix k in n and epsilon greater than 0. And epsilon greater than 0. We can find a partition such that U of Fp minus L of Fp is less than epsilon by k. This is because we are assuming that the function f is Riemann integrable. Okay, how does this help? What is U of Fp minus L of Fp? It's just summation capital Mi minus small mi delta xi. This is less than epsilon by k. Right? This is less than epsilon by k. How does this help? Well, observe the following. Because this is less than epsilon by k, there cannot be too many intervals coming from the partition. So let's make that precise. Let's say P is x0, x1, ... xn. There cannot be too many intervals xi plus 1 such that the terms capital Mi minus small mi is too large, because we have controlled it by saying that the net sum is less than epsilon by k. To make this precise, we already know that epsilon by k is greater than UFP minus LFP is greater than summation capital Mi minus small mi delta xi, which is greater than or equal to summation capital Mi minus small mi delta xi, where I'm going to sum up over bad. What do I mean by sum up over bad? Where bad, let me put this in quotes, is those intervals such that those intervals determined by the partition, of course, those intervals determined by the partition P that have an element of dk in its interior. Okay. So essentially, if you sum up over all these intervals, you will get the entire sum UFP minus LFP. What I'm doing is I'm only summing up over those intervals such that there is a point in the interior where there is an element of dk. That means a point where the oscillation is greater than or equal to 1 by k. Now, why am I doing this? Well, because now this term will be greater than or equal to summation over bad 1 by k delta xi. Right? Now, how does this help? Well, we already know that the original quantity was epsilon by k. Right? So what we get is summation over bad delta xi is strictly less than epsilon. Right? Seems like a miracle has happened, but nothing much has happened. All that has happened is k and k have gotten cancelled. Okay. So what we have got is we have got we have got a collection of intervals xi plus 1, where I comes from the bad set, okay, I will just, instead of belaboring the point, I will just say coming from the bad set, that cover all those points of decay that are in the interior of one of the intervals determined by P. Okay, so what about the rest of the points of decay? Well, the rest of the points of decay, if any, there might be none, if any, are coming from P, right? Either a point is going to be in one of the interiors of one of the intervals determined by this partition, or it's going to be an endpoint. The endpoints are precisely the terms and the elements of the partition P, right? This is a finite set. Okay, so putting all this together, dk is a set of measure 0. Okay, so the crux of this part of the proof was just that we already have good control over the behavior of UFP minus LFP. So the collection of intervals that happen to have a point of decay in its interior, the lengths of those intervals cannot be too large because we have already controlled for it by making UFP minus LFP less than epsilon by k. Excellent. Now on to part 2, which is to show that if each dk is a set of measure 0, then f must be integrable. Okay, we have to show this. So again, we are going to use the criterion for Riemann integrability, that there is a partition P such that UFP minus LFP is less than epsilon. If I can find such a partition, then the function is Riemann integrable. So fix epsilon greater than 0. We have to find a partition P such that we have to find a partition P such that UFP minus LFP is less than epsilon. So now the crux is we have some control over the discontinuities. Away from the discontinuities, the function is nice. It behaves nicely. So we are going to do a proof by cases, but it's proof by cases in a subtle way. We are going to deal with various points depending on whether it's a point of continuity or a point of discontinuity. Depending on what it is, we are going to deal with it in a different manner. So it's sort of a subtle proof by cases. So what we do is the following. First, each dk is a set of measure 0. So first choose k so large that 1 by k is less than epsilon by twice b minus a. Now, I don't like such magic constants, but here it's sort of unavoidable. As it is, the proof is a bit technical. You will understand why twice b minus a in a moment. Okay, so I'm going to first choose k so large that 1 by k is less than twice b minus a. Okay, now since dk is a set of measure 0, I'm going to pull another magic constant out of a hat. We can find an open cover, countable open cover consisting of intervals. Let's call this fancy O, such that the net length the net length of these intervals is less than epsilon by 4m. Okay, what is this capital M? Where capital M is actually going to be supremum mod f of x, such that x comes from AB. Such a supremum exists because the function f is a bounded function. Okay, so I'm going to take the maximum modulus value of this function f, and I'm going to choose an open cover of dk such that the net length of those intervals is less than epsilon by 4m. Okay, again another magic constant, but bear with me for a few minutes, maybe 10-15 minutes, and you will understand where these constants are coming from. Okay, now here comes the crux of the proof. What we are going to do now is we are going to control the behavior of the function away from the set dk by using continuity. The way we are doing this is the following. For each point x in AB minus dk, we can find an open interval Ix such that the oscillation at x of f is less than 1 by k. Okay, such that, rather, we already know this because that's how x was chosen. We can find an interval ik such that the supremum, as x ranges over ix, not x ranges over ix, y ranges over ix, f of y minus infimum as y ranges over ix, f of y is less than 1 by k. Okay, because you are taking a point x which is outside of dk, the oscillation at that point has to be less than 1 by k, which means you can find an interval, small interval ix, that contains x, of course, such that x is an element of ix. That interval ix contains x, and moreover, when you take the supremum minus the infimum is less than 1 by k. This is just the definition of oscillation. Just the definition of oscillation. Okay. Now we can do this for each point x in AB set minus dk. Okay. So for each just a second. For each x in AB minus dk, choose such an ix. Okay, let me just call it some fancy I, be just by definition ix such that x comes from AB minus dk. Okay, now here is the thing. This fancy I union this fancy O is an open cover of AB, right? That's because this fancy I covers all those points in closed interval AB that are not in dk, and dk is already covered by the intervals which are in O, right? So this I union O is an open cover of AB, but closed interval AB is compact, and hence has a Lebesgue number. So recall from our extensive study of topology that there will be a Lebesgue number. What does this mean? This just means this is just a number. Lambda greater than 0 such that any bx lambda is going to be a subset of O which is there in I union O. Okay, So of course x comes from closed interval AB. It's a Lebesgue number is just the number lambda such that if you take the ball of radius lambda centered at x, where x comes from AB, this is going to be contained in some one or more of the elements of the open cover. So there will be some O in fancy I union fancy O which contains this. Okay, that's the definition of Lebesgue number. Okay, now here comes the crux. Now choose a partition P such that successive points are less than lambda distance away. Okay, so this is called the size or the mesh of the partition. That is the least successive distance, sorry, not the least, the largest successive distances determined by the partition. That's called the size or the mesh. It's good to know this technical term, but it's not very it's not going to play a huge role other than just being a terminology. Okay, so what we are doing is the following. You have this AB, you are choosing this partition in such a way that no 2 points, successive points, are greater than or equal to lambda distance away. They are all less than lambda distance away. Okay, so let II be an interval determined by the partition. Okay, since the net size of this interval is less than lambda, it is clear that this II is going to be a subset of O, which is there as an element of fancy O union fancy I. This is the key. So each one of these intervals determined by the partition is going to be a subset of some element, it's going to be a subset of some element of the open cover O union I. Okay, now let's get back to the business of estimating UFP minus LFP. So UFP minus LFP is just equal to summation capital Mi minus small mi delta xi. Okay, so you break this sum into two pieces. You write this as again summation over bad capital Mi minus small mi delta xi plus summation over rest capital Mi minus small mi delta xi. Okay, you're summing up over these intervals and I'm saying you break it up into two parts, the bad part and the rest part, where the bad part comes from those intervals II such that II is subset of O, which is an element coming from script O, fancy O. Okay, the part that is there coming from cover of DK. Now it might happen that some of these intervals II are there as a subset of both an element of fancy O as well as an element of fancy I. In that case, just make a choice arbitrarily. It really doesn't matter. Okay, it really doesn't matter how. Just make sure that each interval appears only once. When you're doing the split up, some intervals might belong to both. That can happen. Okay, that can happen. Because of redundancies, that can happen. Those cases, just deal with it arbitrarily. It really doesn't matter. Okay, excellent. Now, how does this help? Well, think about it for a second. We already know that the sum of all the intervals of this script O, this fancy O, is less than epsilon by 2m. Now you might understand why we put epsilon by 2m. Look at this first term. This first term is certainly going to be less than or equal to 2m times summation over bad delta xi. Okay, where did I get 2m from? Well, capital Mi minus small mi can at the max be 2m, where m is the supremum of mod f of x on the whole interval ab, right? And this we already know is less than 2m times epsilon by 2m, which is equal to epsilon. Actually, I think I made it 4m. I made it 4m for precisely this reason. For precisely this reason, which is epsilon by 2. Okay, so we have controlled the first term, the bad part, by controlling the behavior of delta xi. Okay, now for the rest of the terms, what do we know? We know that capital Mi minus small mi is certainly going to be less than, let's see, it's going to be less than 1 by k. It's going to be less than 1 by k. So these terms, summation over rest, capital Mi minus small mi delta xi is certainly going to be less than 1 by k. Okay. Actually, it's not just 1 by k, it's b minus a. It's b minus a by k. Where does this b minus a come from? Well, it's the sum of all the delta xi's that can be at the max b minus a, because we are probably going to sum up over not all the intervals. Some of them would have gone in the bad part. Okay, but we already made k so large that 1 by k is less than epsilon by twice b minus a. So this will be less than epsilon by 2. So net upshot is u of fp minus L of fp is less than epsilon. Hence, f is Riemann integrable. So again, a challenging proof, but there is a nice idea of balance in this proof. Please go through the details in the notes where I have written out all the details. Of course, for the purposes of the lecture, I have to just skip some of the details. So please go through it again. This is a complicated theorem. In the next module, we are going to see several consequences of this. Pretty much all the standard theorems will fall in your lap with no difficulty. This is a course on real analysis, and you've just watched the module on the Riemann-Lebesgue theorem.